Chapter 19, Part 2. A vengeance-seeking warlock has myopia, nearsightedness. The far point of his left eye is 200 centimeters. What prescription lens will restore normal vision? We were saying before, we were also assuming that warlocks have human eyes. Our S is going to be infinity. That is our normal far point. That is the far point of normal vision. We got that from this first page. That's where we got the 25, and this is where we're getting the infinity. S, our normal vision has a far point at infinity. Our image, S prime, is going to be at minus 200 centimeters. That is our warlock vision. What we're doing with these lenses is a person can't see something where it is. So we're putting a virtual image at a point where their eye can see it. It's actually really interesting. That takes a minute to understand. But they're actually putting glasses put an image where a person can see it. We're going to use 1 over S plus 1 over S prime equals 1 over F. One over infinity plus 1 over minus 2 meters. Remember that your virtual image is negative. Your S prime should be negative. That is going to equal the power. The equation for power, remember, is power equals 1 over focal length. The 1 over infinity is essentially 0. 1 over a huge number is essentially 0. So we're just going to pretend that that's a 0. And we get that our, so you can think of it as writing this out as 0 plus 1 over minus 2 is equal to the power, giving us a power of minus 0.5 diopters. For those of you who wear glasses, if you're in your 20s, you're more likely nearsighted than farsighted. So if you know your prescription, most people in their 20s probably have a negative prescription. Last time I had contacts, it was like negative 2.5 or something like that. So most people would have a negative. So if you have glasses and you are nearsighted, you probably have a negative prescription. If you have reading glasses, those are a positive. Those have a positive power. So if you are nearsighted, then your glasses are a diverging lens. If you are farsighted, then they are a converging lens. Not that you would really need to know which kind of lens, but that's where that sign comes in your glasses prescription. The easiest way to magnify an object is to get closer to it. However, the closest that you can get to see an object is at your near point, around 25 centimeters. What we see in the top set of boxes is a magnifier. The object is placed just in front of the focal point. The height of the object and the focal length, the height of the object and the focal length give us a triangle where tan theta equals h over f. And if theta is small, then we can say that theta is approximately equal to h over f. That's what we get with a magnifier. Now we have the object with the unaided eye. That's down here. This object is placed at the near point, at 25 centimeters. This also gives us a triangle with the sides of h and f, where in this case the f is equal to 25 centimeters. Using the same logic as before with the small angle approximation, we can say that this theta of the object is equal to h over 25. Theta and theta 0, or theta and theta O, are called the angular size of the object, of the thing that you're seeing. A larger angular size is something that's bigger. A small theta or angular size is smaller. The key to magnification is that theta, this theta here, and this theta here are not the same. With the lens, the light rays cross the axis earlier. This creates a larger angle, a larger theta. It's slightly exaggerated here, but if you look, you can see that this theta, this angle, is larger than this angle. This creates a larger theta, so this gives us a larger angular size when we are looking at it through a magnifier. So what it's saying is, since this crosses early, this is more slanted, which gives us a larger theta. Larger theta gives us a bigger object, a bigger thing that you see. We can use this difference in angular size to find magnification. Magnification M is going to equal the magnified angular size over the object's angular size. This here is the object's angular size. You can see that it's smaller. This angle is smaller. And this is the thing that we see with the magnifier. That's larger. For each theta, we plug in h over f. H over f from here is going up top. H over f from here is on the bottom. Note that h is actually the same in both of these. I know that this doesn't sound like it makes sense, but if you trace it through, it actually does. Even that you see something that's larger. This h is the same in both of them. It's just the length of it's just the f length that's changing. So we can cancel this h. That leaves us with a magnification M is equal to 25 centimeters over f, the focal length. What happens is the angle that we're seeing up here, even though the H is the same size, we're not seeing it there. We're seeing it where our eyes trace it back to. We're seeing something with this angle way back here. That makes it look much bigger than it is. A microscope is a two-lens system for magnifying an object. What we were looking at before was closer to a magnifying glass. There are two lenses. They're called the objective lens. The objective has a focal point of FO. And then there's the eyepiece. This has a focal point of FE. The tube has a length of L. In a microscope, an object is placed just beyond the focal point of the objective lens. We have our object right here. It's a very small little arrow. We've got our objective lens. The object is placed just beyond that focal point. Our three principal rays come from the object, and this creates an enlarged, inverted, and real image at the focal point of the eyepiece. Rays that go through the focal point emerge parallel. This is the image that you see. The magnification created by an objective lens has the notation of lowercase m sub o. I'm going to say sub-zero out of habit, but that's an O. That's why I hate using that variable. M sub o is equal to negative L over F sub o. We get this using the same logic as from the page before, where it was a ratio of the focal lengths. The magnification for the eyepiece is capital M sub E is equal to 25 centimeters over F sub E, which is the focal length of the eyepiece. This gives us a total magnification. As those two combine, we get a magnification, this is what's supposed to be by the hard arrow, of M equals MO times ME. We're multiplying these magnifications together, and we get a total magnification of minus L times 25 centimeters over FO times FE. That is our total magnification from a microscope. That will do it for part 2. I will see you in part 3.